Hello everybody, welcome. We're in Module 6, and in Module 6 we're going to dive a little deeper into hardware. We're also going to review things we've already learned about hardware. So we're going to go over these things here. You could pause the video, you could read about it. We're also going to go over these things here. You could pause the video and you could read about it. And again, some of this stuff's going to be reviewed, but some of it will be new. And either way, it's going to deepen your knowledge and reinforce your knowledge so that you become stronger and more knowledgeable and more skilled with computers. So the first thing we're going to talk about is Moore's law. And so technology is always advancing. And there's this law right here. You can see it graphed, and we'll talk about it in a second. But it's created by this guy, Gordon Moore. And so Gordon Moore is one of the founders of a company called Intel. And Intel makes CPUs. It makes circuits. It makes chips, silicon wafers. And so this is really the brains of a computer. And these are the silicon wafers. And on these silicon wafers, this is a wafer. And then on this wafer, they'll cut out all these little squares. And those will be the chips that go into cell phones and go into computers. And on each of these chips, integrated into them are circuits. So they've integrated circuits on these chips. And if you remember back to our earlier discussions about how a computer works, a computer is like your porch light on Halloween. Your porch light on Halloween, because your porch light has a light switch, and that light switch could be on, right? It could be on or it could be off. And if that light switch is on Halloween in America, it means come trick or treat. And if that light switch is off, it means go away. And this is really the fundamental idea behind how computers work. We have a switch, like a light switch, and you could also refer to that as a circuit, and it could be in an on state or it could be in an off state. And if it's in an on state, it means one thing, like come trick or treat. And if it's in an off state, it means something else, like go away, don't trick or treat here. And so that's called a coding scheme, where a switch in either an on state or an off state, we could associate some meaning with that, whether it's come trick or treat, go away, or the letter A if the switch is on, and the letter B if the switch is off. And so this is how computers work. And way back in the early days, like in the 60s and 1971, Gordon Moore helped create the first chip, the first integrated circuits into silicon, right? It's the first silicon wafer chip. And the 4004, so we could ask ChatGPT here. So I'm just looking for, like, where's my chat box? So maybe I have to hit refresh here. Let me hit refresh. And my chat box isn't showing up. I don't know why. And this is, so maybe it's hiding down beneath this. Let me just bring that up. There it is. So I just need a little bit more room there. And so we'll ask ChatGPT, how many circuits were on the Intel 4004 chip, and when did that chip come out? So we'll ask ChatGPT that question. 4004 came out November 1971, and they were able to put 2,300 transistors. So you could call it a switch, like a light switch. You could call it a circuit, or you could call it a transistor, right? So you can see here it's called a transistor or a circuit. They were able to put 2,300 circuits, like a light switch, right? Which could be in an on-off state, and you could check, is it in an on state or an off state? You could check that. They were able to put 2,300 of them on something the size of your pinky fingernail, which is pretty extraordinary. And so over time, that the amount of circuits that they could put onto a silicon wafer chip has increased. How much has it increased? Well, the 4004 right there had how many? 2,300, right? That's the 4004 in 1971 had 2,300. Well, that's in the thousands right here. And then that has increased. They were able to get 16,000 by the mid-70s. By the 80s, they were able to get 256,000 circuits, which could be checked on something the size of your fingernail. They could check them. By 1980, they had 256,000. Then they got up to the millions, and then they got up to the billions. And now they're at 128 billion switches, circuits, transistors could be put on something the size of your pinky fingernail, and they could check each of them, which to me is very mind-blowing. But one of the implications of this is that Moore's law says that every 18 months to 2 years, the processing power of computers is going to double. And so here you could see, right, if we are at year 0, the current processing power of our computer, let's just call it 1. And if we go 2 years, then new computers will be twice as powerful. And if we go 2 more years to 4 years, new computers then will be even twice as powerful as that. So they'll be 4 times as powerful as your computer just 4 years ago. And if you go 2 more years to 6 years, right, computers will be twice as powerful. So in 6 years, new computers will be 8 times as powerful as your computer was that you bought 6 years ago. And if you go 8 years, new computers will be 16 times as powerful as the computer that you purchased 8 years ago, right? It'll be 16. And if you go 10 years, right, new computers will be 32 times more powerful than the computer you bought 1 year ago, or the computer you bought 10 years ago, right? Which can only do 1x. So as computers become more powerful, the software that's written for them is written to take advantage of that power. So if your computer is 6 years old and current software is written to take advantage of something that could process at 8x, and your computer is processing at 1x, then just like real simple mathematics, this new software is going to ask your computer to do stuff, your old computer, that new computers that are 8 times more powerful can do more easily. So your computer is really going to struggle to do that because it doesn't have 8 times as much processing power, which is what the new computers have. So you could just, like, as a general rule of thumb, say it's going to be like an 1/8 less powerful. So it's going to take 8 times more to do the processing that's asked of it. And so it's just going to be slower, right? And that's why after 5 years, 6 years, technology is kind of like, wow, that computer's starting to get slow. Well, that's because new computers are so powerful, and after only 5, 6 years, and the software that's being written for them is being written to take advantage of that power. And so your computer can't process all of that. It's asking too much of your computer. So that's Moore's Law. And the basic takeaway of Moore's Law is that technology doubles every 18 to 24 months. We could ask ChatGPT, can you please explain Moore's Law for me? I guess that's it. There we go. I guess I should put a question mark after that. Moore's Law is observation by Gordon Moore, co-founder of Intel, in 1965, which states that the number of transistors on a microchip doubles approximately every 2 years, while the cost per transistor decreases. In essence, this means the processing power of computers increases exponentially over time, while the relative cost of computing decreases. So you could pause the video and you could read through the rest of that, but that's Moore's Law. So now we'll also talk about things to consider, like, with emerging technologies, computers are getting faster. There's more processing power on the silicon wafers. And then there's different components, which we'll talk about, like DRAM and the hard drive, and that's all coming up. And so DRAM stands for dynamic RAM, and dynamic RAM is just another way to refer to the RAM that we normally talk about. And that's a differentiation from static RAM. And just so you have that information about the difference between DRAM and static RAM, you could pause the video here and you could read about DRAM. And this gets a little bit into the details, the weeds, like a little too much specifics here for what I feel you need to know just out in the world. But if you really like to know the details of computers, you could pause the video here. But just as a basic, DRAM is a type of computer memory used to store data that your computer is actively using. It's a common form of volatile memory, meaning it needs constant power to retain data. Once the power is turned off, the data stored in DRAM is lost. And how do we compare that to SRAM? SRAM is a type of computer memory used for high-speed applications like cache memory. So it's really, SRAM is the stuff we've talked about as cache, and DRAM is the stuff we've talked about just as RAM. So that's the basics of it. All right, moving on to the next slide. There's different computers, different sizes of computers. These are all computers, but we've talked about this already a little bit, but it's good to reinforce, right? Smartphones, tablets, 2-in-1s, laptops, desktops, right? These are all using the same sort of idea of how computers work. They're all computers. They all have a CPU. They all have RAM. They all have some sort of storage in them where you could store stuff permanently that's non-volatile. So volatile means that when the power goes out, whatever was stored in those areas of remembering inside of a computer whatever was stored there is forgotten. It's volatile. Non-volatile means that when the power goes out on the device, whatever is stored will be remembered. That's non-volatile storage. But these are all different computing devices. Now we're going to talk about the CPU. We've seen in previous lectures, we've learned about the motherboard, and we saw the CPU on the motherboard, but just so you could reinforce that, CPU motherboard, we could just like Google that and go take a look at it. And if we look at a motherboard, we'll see like here's a CPU being set on a motherboard, but here's a motherboard right here, and the CPU would go right there, right? And here are images of what some CPUs look like, and they have pins. And then the pins, so here you can see the pins push into the motherboard, connecting the CPU to the motherboard. And then here's a diagram of all the different aspects of the motherboard and where you connect different things. So that's the CPU. It's located on the motherboard. It processes the instructions. It's the brain of the computers. Central Processing Unit is what CPU stands for. It performs calculations, and it manages the flow of information, right? So where and when should different information come into the CPU to be calculated? The CPU also manages that. And Intel and AMD are two of the large manufacturers of CPUs. You can learn about your computer and how your computer is operating by going and looking at, here in Windows, you could go to About Your System, and you could check that out. And on a Mac, I could come to this little area, the Spotlight Search, and I think it's called Activity Monitor. There it is. And I could launch the Activity Monitor. And so here's the Activity Monitor. Let me bring it over to where I'm recording. And it shows me that right now my system is using 5% of my CPU, and the user, me, I'm using 8% of the CPU. And for a total, like 85% of my CPU is idle. If I was to do more stuff on this computer, and I could also see how the memory is being used, right? So I'm using 21 gigabytes, 22 gigabytes of my 36 gigabytes. So looking at this can kind of tell me that when I get my next computer, maybe I want to get more than 36 gigabytes of memory because I'm already at 22 and I'm just running a bunch of tabs and I'm recording a video. And I really feel like I'd rather, have more memory so I could do more stuff. And likewise, you could look at energy use, you could look at your disk use, you could look at your network use. And so you could see all these different things here on the Mac in the Activity Monitor. But if this was on Windows, you would check that out by looking at About Your System. So that's useful for helping you determine like, hey, do I really need a more powerful CPU or do I need more RAM? And just looking at this right here, it's like, okay, next time I get a computer, I'm getting more than 36 gigabytes because what I'm doing is already using 21 gigabytes and I don't feel like I'm doing that much. So I'm going to get more RAM next time I get a computer. The way a CPU works is it goes through a machine cycle, and these are just the basics of how a CPU works. And to truly get, great understanding into how CPU works, you have to, study it for many, many years and become an engineer. And other than that, for the vast majority of us, it's a black box, which just does the processing. But we could get some of the high-level ideas of what's going on in there. And so here's the CPU, and then inside the CPU, you have different components. You have a control unit, and you also have arithmetic logic unit, and then you also have registers, and then there might also be cache in your CPU, and that's CACHE. And cache and registers are part of computer remembering, where the computer can store data temporarily and access it really quickly. We saw that in a previous video lecture. And so that's the remembering part of a computer. And we learned why it was important for computers to remember stuff. And we did that with the math problem. What's 2 plus 17? What's that equal to? That's 19. But to do that problem, I gave you input. So, and you received that input. And then you stored that input, 2 plus 17. You stored that. And then you processed it, and then you output it. If we were talking, you would have said, oh, that's 19. You would have output it. And those 4 basic functions are the 4 functions of a computer: input, process, store, input, storage, IPOS, input, processing, output, storage, though we talked about it as input, storage, processing, output, because that's the order in which those things happened. And so that's why computers have to remember stuff. That's why we have to remember stuff. Because as we receive input, we have to remember it, and then we take those little pieces and we process it. Well, we're holding little pieces in memory somewhere. We're remembering it somewhere. And like just like us, a CPU will hold little pieces 2 plus 17. It'll hold those pieces while it's processing, and then it'll give it to the arithmetic logic unit. Add this up, 2 and 17. And it'll get the answer 19, and it'll store that, and then it'll push that back out maybe to RAM, and then that will get output to the monitor, to speakers, right? And so then the control unit's going to control how is everything operating in the computer, who has access to the CPU, which programs should process data, and in which order. The control unit's going to help control that. So those are different aspects of the CPU. And again, we talked about this pretty in depth with a previous lecture where we saw that diagram of computer remembering. So that's a little bit about the CPU. And if you want, I really encourage you to go to ChatGPT if you want more insight into that. And I think I might have asked this question when I was in class. Look, 77 references to CPU here on this. But let me just see if I asked a question about the CPU. And so, wow, lots of references. Can you explain the basics of how a CPU works? Here we go. So you can pause the video right here if you want to read about that. And then you could also pause the video right here to read more about that. And then you could pause the video right here to read more about that. And so that's a little bit about how CPUs work. And CPUs also use, different kind of architectures for processing more quickly. And so some of those different things they do are parallel processing, multi-threading, pipelining, and hyper-threading. And again, this is like a little bit of a bridge too far for us. It's a little bit more detailed than we need to really get in this class. But just to give you an idea of what some of this stuff is that in 2005, they released, 2006, the first commercially available computers with multiple cores. And so one CPU could have multiple cores where multiple processing can be occurring in different cores at the same time. And so today's computers come with multiple cores on them, the vast majority of them, if not all of them. And that allows us to do parallel processing. And so this is really different than serial processing. And I'm talking about serial as like this, right? Serial processing. So serial, that kind of a cereal right there, not the kind you eat for breakfast, but serial as in one at a time. So serial processing would be that everything is being processed in a single fashion line, one after another in serial. So if you had one CPU, everything has to be processed one after the other. That's the only choice. It's like a single one-way road where each car has to go right behind the other car. There's no other option. That's serial. Parallel processing is like a multiple lane freeway where all the cars are moving in parallel at the same time. So with parallel processing, when you have multiple cores, you could have different processing occurring at the same time going through different cores. And so that's parallel processing. It's all happening in parallel, like many cars on a freeway with many lanes. They're all traveling in parallel. Likewise, with multiple cores, parallel processing going through all the cores at once. And when you write computer programs, you can write programs in some languages, like the Go programming language, for instance, which YouTube is written in and a lot of Google is written in. But with the Go programming language, you could write code using concurrency design patterns. And concurrent means happen at the same time. So concurrent design pattern means that you've written your code in a concurrent design pattern so that if it runs on a machine with multiple cores, that concurrent code could run in parallel. But if you take your concurrent code and you run it on a machine with one core, then that code is going to have to run in a serial fashion, one after another, because there's not multiple cores to take advantage of, right? So that's parallel processing versus serial processing, and then that's concurrent design patterns in programming. You write concurrent code, and then if it runs on a machine with multiple cores, it could run in parallel. So those are some of those terms. And then multi-threading is the ability of a single CPU to manage and execute multiple threads of instructions concurrently. And pipelining is a technique in CPU architecture where multiple stages of instruction execution are overlapped. And hyperthreading is like multi-threading and pipelining combined. So it allows simultaneous multi-threading on a single CPU. So that stuff is a bit more detailed than we really need to get in this class. Though in the next couple of slides here, you'll see that. And so here you have an example of, quad core. And so there's 4 threads going through this CPU at the same time. And we have parallel processing, right? So yellow would be music, blue would be your web browser. This would be a virus scan, this would be gaming, and they're each going through 4 cores. And then here's an example of like pipelining, where you have this machine cycles overlapping as they're being executed. And then here is an example of hyperthreading, where it just looks like a jumbled mess, where you have a lot of stuff executing in multiple ways all at the same time, and that can improve performance. And so when you're evaluating your CPU, if you really are going for performance and you're a quote-unquote power user, like maybe you're a video gamer, you want to have a higher clock speed. So the clock speed is how many instructions can be processed every second. So those are measured in gigahertz, and that's billions of instructions a second. So like a 3 gigahertz CPU can execute 3 billion instructions a second. So you want a higher clock speed if you're a power user. You want more cores if you're a power user. You want more cache memory and more RAM memory if you're a power user. And then you also could take a look at CPU benchmarks, which measure like how fast are different CPUs at performing the same task. And so you could see, which CPU is more powerful. So that's a little bit about CPUs. And now we're going to talk about memory. And we have RAM, which is short-term memory storage. It's volatile, so the power goes out, you lose it. We've already learned about this. We also have ROM, which is where BIOS, basic input-output system, is stored. And it's critical to the startup process. It's where the startup instructions, BIOS, are stored. And it's non-volatile, meaning the power goes out and what's stored in ROM is still there. Here is the books picture of computer remembering, where you have different levels where things can be remembered in your computer. And up here, you're closer to the CPU, and the CPU can access things here faster, but you could store less, which is why this is smaller up here than down here. And down here, you're farther from the CPU, so access is slower, but you can store a lot more. And so, as you move up this, you get closer to the CPU, you could store less, but it's a lot faster. So this is fast access, but less storage. This is slower access, but more storage. And then here's what RAM can look like. And, there's different, kind of iterations and names that RAM has gone through. And if you ever see DIMM, it's a dual inline memory module. That's what that stands for. Other things to know about memory, we saw how to evaluate and monitor your resources here on my Mac. But something else is like the CPU will often preload what it thinks you're going to need. So it could get it closer to the CPU. So if you do need that, it's ready to be there to be processed. And we learned about resource monitoring already. You could always install more RAM, but it's kind of like just like if you have a BMW or a Toyota, you want to put BMW parts into a BMW and Toyota parts into a Toyota. If you're going to install more RAM, you have to kind of look up what kind of computer you already have and what type of RAM you should buy, because there's different types of RAM out there, and you want the stuff that works in your machine. Put the Toyota parts in the Toyota, put the BMW parts in the BMW, and so that's something you also have to do. And there can be issues, like I tried to put too much RAM into a computer recently, and Windows couldn't deal with it, and I had to take half of it out, and then Windows ran fine. So sometimes there's just issues you can't control. Here's what a hard disk drive looks like. So it has platters, and then it has these little read-write heads right here, and they'll read and write to both the top and bottom of each of these platters. And so this is where positive and negative charges will be stored to represent those on-off 0-1 states. And that's how they work. And this is a moving part. So it's actually a point of weakness and vulnerability for computers because it is moving. it's not as robust and durable, as opposed to a solid state drive, which has no moving parts and is therefore more robust and more durable. So here's solid state drives, and they're faster, they're more robust, they're quieter, they use less power, they generate less heat, and they're more expensive. Here's a little diagram about, trying to evaluate how much storage you might need. And so this is just an idea that somebody came up with, that's like, what are you going to run? But basically, you get a sense of this over time, and that sense will inform you about, how much you might need. So I do a lot of video editing, so I know I'm going to need a whole lot of storage and a lot of RAM, and more of a power user. And so I'm going to get systems that have, higher clock speeds on the CPU. They're going to have more RAM. And they're going to have a solid state drive, so I could store stuff on that when I'm working with it. And it'll also have a hard disk drive for long-term storage, just to put stuff, and it'll be there if I ever need to go back and get it. And so, but here's a diagram of just evaluating for some user how much storage they might need in two different scenarios. If you need even more storage, or you're at like the corporate level and you need to back things up, and maybe have mirrored redundancy of all the data, you could put in a redundant array of independent disks. And then there's different patterns that you could use for how you store stuff. So this is like called striping or something like that. It's been a while. And so here you can see you're storing some of the stuff. If this is all the stuff you need to store, you're storing some of the stuff on this drive and some of the stuff on that drive. And if this is all the stuff you need to store, here you're getting backups. You're storing it all on this drive. You're also storing it all on this drive. So if this drive fails, you have it all right there. Evaluating a storage subsystem, right? Like you could use mechanical hard drives if you just need long-term storage, because these are relatively inexpensive and they're slow, but you can store a lot for a little amount of money. Solid state drives if you need to store a lot and have it more readily and quickly available. Solid state hybrid drive, which is kind of a combination. I don't really do that. I just like these two, one of each or a couple of each. And you could also store stuff on the cloud, which is really useful because all of your email and pictures and all that should be cloud-based. So if you lose your computer, you could get a new computer, swap out your drives, transfer the stuff into the new computer, and then you're ready to go. And then we have media. And so some things to think about with media. You've got your video card and you have your monitor. And then you also have different ports. And so you have HDMI. And so HDMI port looks like that. And then you have a display port, which looks like that. And then you have DVI. So this one's old. This one's pretty good. And that one I think is the best. But I'm not totally confident. So display port, HDMI, and DVI, we could say, can you rank these from newest to oldest? And we'll do display. We have DVI, oldest. And then we have digital video input. We have HDMI and high definition media input. I think that's what that stands for. And then we also have a display port. And a display port, pretty self-explanatory. I'm just making sure I got those. Display port, HDMI, DVI. And then we'll also ask it for newest to oldest. Should have been oldest. DisplayPort was 2006. DVI was 1999. HDMI was 2003. DisplayPort was 2006. So if you just go by Mosquito, if you just go by this idea that newest is best, you kind of want to go with DisplayPort. And so there you go. And then we have video memory, screen resolution, and graphics processing unit. This is a really nice, kind of diagram. If you're trying to push everything through here, your CPU, the CPU could get bogged down without a GPU. But with a GPU, you could take all of your things that are related to your graphics. So this is central processing unit. And this is your graphics processing unit. And it's designed for processing graphics. And you could run all of your graphics processing through that, which is going to make your computer more performant and better at like video games and video editing. And so we asked in class a lot about GPUs, and I think that was right up at the very top. So let me just scroll up to that and we'll get some stuff. So here is how monitors work. And we've talked about this before, but just so you could review it, there are pixels, there's color depth, and there's refresh rate. And then here, you can pause the video and read about all that. And then here's the graphics processing unit and frames per second response time. So you could pause the video and you could read about all that. And then here's a summary of all of that. So you could pause the video and you could read about all of that. And then here's a little clarification on 8-bit color. And you can pause the video and read about all that. And then also pause the video and read about that. And then a student in class asked a question, at what FPS does it become ridiculous, no longer choppy, but you no longer really notice? And so here's a little bit of explanation about that. And so that is all about monitors and the GPU. And so here's a little bit more about the GPU and what it does. So you can pause the video and read about that. It's good to know about. And then here's a little bit more about parallel processing and gaming and frames and smoothness. So you could pause the video and you could read about that. And so GPU, if you go and you look them up, right, like GPU, and let's look up a GPU and images, and this big thing, look at how big that is. And it's got its own fans, and these can cost like $700 to $1,500 or common prices for gamers to pay. And you can see those prices here. But you could even go up to even more insane prices for the really high-end stuff. But the GPU is going to help your computer really process images. So if you're editing videos or if you're playing video games, it's just going to make that entire experience way smoother. And you would plug this into your accelerated graphics port. You'd plug that in right there. And then when you plug that in, it will have ports on the back of it where you could then plug in your monitors. So the back of the GPU would have ports, and I'm just looking for another one here. And so here are these ports, and you'd plug your graphics card into like one of these, and its ports would be exposed out here on the motherboard, and then you could just plug in, you could plug in your monitors into your display ports. So here's an example of what that looks like, right? So here you have your other ports, and then you plug in your GPU, this massive thing, into the motherboard. And then you have, here you have HDMI, and here you have DVI, and maybe those are display ports. That's what they look like. So that's like what that looks like, and that's going to improve the speed of your computer. And it'll have video memory, it'll increase the screen resolution, and it'll be your GPU. And then we have speakers and sound, and you could really optimize your sound, surround yourself with speakers to make it sound beautiful. And MIDI, and I'm not sure if MIDI is still relevant. That kind of surprised me, the book was talking about it. Is MIDI still relevant today? And if so, how? MIDI is still highly relevant, especially in music. Although it was first introduced in '83, it means a fundamental tool because it allows electronic musical instruments and other devices to communicate with each other. Okay, because I associate MIDI with just like really tinny old sounds, but MIDI allows communication between different sound-producing electronic devices. So you can see a picture of that right there. Other things to think about here, the reliability of your system. Make sure you're running an antivirus program. Have spyware and adware if you're having issues with that. Clear out unnecessary files. This mosquito. Run disk defragmenter. That's not so relevant today unless you have a hard disk drive. And automate key utilities. But let's just check this, okay? Let's just go here, because sometimes I'm not sure about stuff. And let's say, do you need to run disk defragmenter on SSDs? No, you don't need to on solid-state drives. In fact, it's not recommended. And here's a reason why you don't need to run on SSDs. You can pause the video and read that right there. And then automate key utilities. So system crashes. So if your system's crashing a lot, you could try system restore. This is super good to know about. So you could go and you could Google any computer. I have a MacBook Pro here, and you could Google how to restore to factory settings, right? Restore to factory settings. There we go. And it'll show you erase your Mac and reset to factory settings. So your computer, all the software, we talked about hardware, operating system, application software, all the software that is sitting on top of the hardware, your operating system and your application software, that could be all thrown away. And you could reinstall your operating system and reinstall your application software. That's a system restore. And you could follow those instructions by Googling what type of computer you have and then the word system restore after it. And then you could restore your system. So that's a good thing to do if your system's crashing a lot. You could, see if maybe you need more RAM. You could investigate error codes, Google them, ask ChatGPT about it, search with Google, and or restore Windows. And getting rid of your old computer, you want to recycle it, and you could ask, like computer recycling, and I'm in Fresno, so computer recycling near me, you could find places that recycle computers and take them in so that they're disposed of properly. Because otherwise, it's got mercury, cadmium, other kinds of things which aren't so good for the environment. And before you get rid of it, you want to make sure you remove all of your personal data so that people don't take your hard drives and try to gather your personal information from it. There's a really good kind of YouTube, and that YouTube was 60 minutes computer recycling. It's kind of old, but still kind of fun to watch. The Electronic Wasteland, 14 years ago. And then there's also the computer recycling here in Fresno. So you could check that out on your own time. Computer recycling here in Fresno is, well, where did it go? They were, there's a lot, but there's one way down here, ERI, Electronics Recycling Recyclers, but that's a business that is in Fresno, and you could see pictures of computers being broken apart and recycled. So, companies will pay to have these computers disposed of in a secure way, and that's what they do. They go through and they get rid of everything. So I guess they're around here somewhere. I don't know where they are. All right, well, that's Module 6. I hope you enjoyed that. Keep doing your work and keep plugging away, and you will make progress. See you next time.